All right, so we're going to continue our conversation about rational functions today. And what we're going to move into is graphing rational functions. Now, there's a lot that goes into graphing rational functions. So what we have done is we have broken this into 2 or 3 different pieces. And we're going to look at various aspects of a graph of a rational function, and then we're going to put them all together. All right, so today's lesson is going to center on finding vertical asymptotes and holes. All right, now you're familiar with vertical asymptotes, but probably not so much about what a hole is. All right, this is also going to transition us from that HK form, all right, into our other form, all right, which is a polynomial over a polynomial, which we looked at last time with some simplification. So to kind of get us moving in that direction, what I would like you to do is graph f of x here. Now this is an HK form, so you should feel comfortable graphing this one. So go ahead and pause the video, graph f of x. We'll go through that, and then we'll compare that to g of x together. All right, so let's take a look at f of x. Now, so when we look at this, this is an HK form, and so what we know, all right, is that we have a vertical asymptote at -2. All right, so I'm going to draw that vertical asymptote in right here, just like so. All right, now our k value is 0 this time, so our horizontal asymptote is at +0. So I'm just going to emphasize that here. All right, and then our a value is 2. So normally in our mother function, from wherever our origin is, or in this case our new origin, once we've put in the vertical and horizontal shift, all right, we would go to the right one and up one. But since our a value is 2, I'm still going to go to the right one, and then I'm going to go up 2. So remember, the a value only affects the y value. All right, and then that would give us this half of our graph here that's going to fit into that upper right-hand portion of our graph. Normally, we'd go to the left one and down one from our origin, or our center here. And since our a value is 2, I'm still going to go to the left one, but now I'm going to go down 2. And then once again, all right, going to follow the asymptote in each direction, and this would be our graph. All right, so notice we can look at this graph. We can see we have a vertical asymptote at -2. We can see the horizontal asymptote at 0. All right, we can use what we know about a values to graph 2 really quick points. All right, so here's the question. What is the difference between f of x and g of x? All right, so now we're going to tie in what we did yesterday, which was, all right, when we look at these rational functions that are not in HK form, what we want to do first is simplify them. So that means factoring the numerator and the denominator completely, just like we did yesterday, and simplifying. Now, if I look at the numerator here, I can factor out a 2 as a GCF, and I get 2 times the quantity x minus 3. All right, now in the denominator, all right, I'm going to factor this. All right, I'm not going to show the method, all right, but I'm going to go ahead and factor this, and then I would have an x and x here. I would have, all right, a 3 and a 2 like this, and this would be negative, and this would be positive. So now this is basically what we did yesterday, all right, in our lesson together, all right. Factor everything, look at it, and then notice right now, okay, what we know right now is we have 2 domain issues. All right, so if we go back to f of x, we knew right now x could not be -2, and that gave us, all right, a vertical asymptote. Now, if I look here, we have 2 different issues because we have 2 different values that makes our denominator 0. So we still have this -2, right? So we know x cannot be -2. But notice x cannot be 3 either, right? So x cannot be 3. And notice this is what we talked about yesterday. Now we have that common factor in the numerator and the denominator, which divide out to be 1. And notice it simplifies into this, which now, when we look back at f of x, it looks very, very similar, right? So notice we get this vertical asymptote at -2 still. So I'm going to draw that in. We're still going to have our horizontal asymptote at 0, just like we did before. All right? Now, I'm going to start on the left-hand side for a reason, and I'll show you why in just a second. Now, I normally would go left 1 and down 1, but now I'm going to go left 1 and down 2. Now I'm going to get this part of our curve, and notice it looks exactly like that part of the curve. Well, if I was a better sketcher, it would be. But those should match up exactly, right? Now, here's where the difference is, right? I'm still going to go to right 1 and up 2 like I did over here. But here's the issue. Notice we said we can't use 3. We can't use 3. Right? We had to throw that out of our domain. We talked about that yesterday, right? It's the beginning of the problem that determines the domain, not the end. So there's an issue here. And this is what we call a hole. All right? So what this means, if I were to plug 3 in here, notice if I were to plug 3 in here, I would get 2 over 5. So it looks like there should be a point at 3 2/5. But notice I can't use 3. So what we do is at 3 2/5, we put an open circle. Just like that. And so what that indicates is that we have a domain issue, right? We can't use that point, even though it looks like it. And so that's what we create, and notice that our graphs are going to look exactly the same. It's going to come down, but now there's just one point right there has to be thrown out. So these are exactly the same. These are exactly the same, except for we have this one extra domain issue, which is what we call a hole. All right? So that is the difference in the two graphs. Now, this is also vitally important why we set the domain in the beginning of the problem. Because notice if I looked at the end of both of these, I would think they're the same. But they're not. All right? There's one key difference, one vital difference, that we lose one more value in our domain. All right? And when we do that, it creates this hole. All right. So that's what we're going to work on today, is this idea of vertical asymptotes and holes. And how do I know the difference between them? All right? And so when we think about what we're doing, right, we know that our denominator can't be equal to 0. All right? And so when my denominator is equal to 0, all right, for those x values, I'm going to have one or two possibilities. The first is that vertical asymptote, which like we've seen before. All right? And that second possibility is the hole. Now, we will get a hole anytime we have this common factor in the numerator and the denominator. All right? That is what creates the hole. It's that factor, all right, that divides out, and the 0 that comes from that factor. A vertical asymptote, all right, will always occur in those values still left that make your denominator 0 in the end result, in that simplified version. All right? So that's what we need to look at today. So we know that once we have domain issues in a rational function, it's either going to be a vertical asymptote or a hole. All right? And it's how we get, all right, there that determines which one is which. So notice we're going to really do exactly what we did yesterday now, right? We're going to factor the numerator. We're going to factor the denominator. All right? We're going to identify those values that make the denominator 0. And then now what we're going to do is now we're going to determine, okay, do I have a common factor with the numerator? If so, that makes it a hole. If I don't, then that's what makes a vertical asymptote. All right? Okay? And then what we're going to do is then we'll find the rest of that coordinate for our hole by plugging the x value in, just like I did from above, all right, to write that coordinate that we could graph. All right, so let's do a few examples together here. So let's flip over to page 125 here, all right, and let's look at number 1 here. All right, so once again, all right, and we only have to do this if it's not in HK form, all right, because if it's in HK form, we know what everything is. There won't be a hole in HK form because it's already simplified, all right. So notice this practice is only if we're not in that original form that we talked about. All right, so when we think about number 1 here, notice we need to factor completely. And like we talked about before, we always want to look for that GCF if possible. And notice we have one here. So I have 3 and then x plus 3 like that. All right. And then in my denominator, I also can factor out a 3. And I get x plus 2 like so. So now when I think about this, right, there's nothing else to factor. All right. And notice now the only common factor is 3 divided by 3, which is 1, which means my simplified result is x plus 3 over x plus 2. So notice I don't have any common, all right, linear factors that cancel out. I have a number, but 3 divided by 3 is just 1, so that's no big deal. So now here's what this means. We only have one value that we can't use, right? So when we think about our domain, it's all real numbers except x can't be negative 2. All right? So that means we only have one domain issue. All right, that's the only value that makes our denominator 0. So it can either be a vertical asymptote or a hole. Well, notice, is x plus 2 common to the numerator? Is that a common factor that we can divide out to get 0? And the answer is no. And so if we do not have any common factors in the numerator and the denominator, we will not have any holes. All right, so what this tells me is that this is just a vertical asymptote. All right, and that vertical asymptote then would be at x equals negative 2. And that's our process. Okay. All right, so now that's all there is. So if we don't have any common factors, all right, linear factors, all right, that are common to the numerator and denominators, we can't have any holes. All right, now let's look at number 2. All right, So now the numerator is, all right, factored all the way, so now I need to factor that denominator. And so just real quick, we can do our area model over here. Right, so x squared goes here, negative 9 goes here. A times c is negative 9. And notice once again we have to add to get 0x. And we talked about this last time, that anytime I'm adding to get to 0x, we know this is what we call the difference of two squares. All right, so what is the square root of 9? It's 3, right? So I need 3 times negative 3. And then 3x plus negative 3x is 0x. So drop that 3 here, drop the negative 3 here. All right, I hope I could get my x's on there. All right, so our GCF in our first column is x. Our GCF in our second column is a positive 3. Our GCF in the first row is x. Our GCF in the second row is negative 3. So I can see that this is x minus 3 times x plus 3 when it's factored completely. All right, so now when I look at my domain, right, I have two values that make my denominator 0. So for my first factor, right, x can't be 3 because 3 minus 3 is 0. For my second factor here, all right, it can't be negative 3. Negative 3 plus 3 is also 0. So there are my two, all right, issues with my domain. Now, once again, do I have any common factors between the numerator and the denominator? And the answer is no. All right, and so then that means I can't have any holes. All right, there's no simplifying that's left for this. So what that means is that both of these values left are going to be vertical asymptotes. And so notice right away that this is different. So now, when we looked at things in HK form, we would have only one vertical asymptote. That's not true anymore. Okay, so now when we're looking at other types of rational functions, all right, okay, we can have more than, all right, more than one vertical asymptote. We could have 2, we could have 3, we could have a lot. All right, so just be prepared. So just understand that you have to actually go through and analyze. You can't say, oh, I've got two domain issues. One's going to be a hole, one's going to be a vertical asymptote. And it's not going to be true, right? It could be one of each. It could be two vertical asymptotes. It could be two holes, depending on what the problem is. All right, so make sure you go through the process and analyze those. Okay. All right, let's move to number 3 here. All right, and this will be the last one we do together here. All right, now, just once again, I'm going to just do the factoring for the numerator and the denominator just on a little bit of another sheet of paper here, just to make it a little bit easier for you guys to see. I can write a little bit larger here. So there's our numerator, and there's our denominator. All right, so if we start with the numerator, there's no GCF to worry about, so I can go right into my area model for factoring. Drop my A term here, my C term here. We're going to do A times C, so that would be 6. We have to add to get to 5x. All right, so two numbers that multiply to be 6 and add to 5 would be 3x times 2x, right? I don't have to have the x's up here, I guess. So, but then 3x plus 2x is 5x. So if I drop the 3x and the 2x into those two slots, the GCF in our first column would be x. The GCF in our second column would be a positive 3. The GCF in our first row would be x. And then the GCF in our second row would be a positive 2. So I can see that my numerator here is going to factor into x plus 2 times x plus 3. Okay, so now let's move to factoring the denominator. All right, now I do have a GCF here. All right, so if I look, right, I can factor a 3 out of all 3 terms here. The other thing is we typically want the A term to be positive. All right, so I'm also going to factor out a negative here to make that so. So I'm going to factor out a negative 3, and notice that would leave me x squared minus x and then minus 12. All right, so remember you have to take that negative out of all 3 terms, right? Okay. Now, once again, notice by factoring in that GCF, that's going to make the factoring model a little bit easier because we're going to have fewer combinations. All right, so I'm going to just do my area model once again. So drop my A term in here, my C term in here. Now, notice, right, my A is 1, my C is negative 12, so A times C is negative 12. And now I have to add to get that negative 1x. So I need two numbers that multiply to be negative 12. So that means one has to be positive, one has to be negative. The only way to get a negative number is to have one of each, right? And then I have to add to get negative 1. So in this case, it would be negative 4 times 3 is negative 12. And then negative 4x plus 3x is negative 1x. All right, so let's drop those guys in. So I'm going to drop the negative 4x in here and the positive 3x in here. And then let's look for those common factors. So in my first column here, I have a GCF of x. In my second column, notice my GCF would be a negative 4. They're both negative there. In my first row, I have a GCF of x. And then in my second row, I'm going to get a positive 3. So now when I look at this, once again, all right, I have my negative 3 out front, and then I have x minus 4 times x plus 3. So remember, I need to take all of that back to our original problem here. So don't forget that anytime you factor out that constant, it's still part of the problem. So now, I'm going to just take all of this over here. So I'm going to have my negative 3, x minus 4, and then x plus 3, like that. All right, so there's our factored, all right, form. Now, once again, now I can look. All right, I've got two issues for a domain here. So my first factor, all right, so my first factor here, x can't be 4. Okay, 4 minus 4 is 0. Now I move to my second factor here. All right, it can't be negative 3. So negative 3 plus 3 is 0. So there are my two domain issues. All right, so now, notice, this time we do have a common factor in the numerator and the denominator. And that common factor is x plus 3. So that divides out to be 1. So what that means is that is going to give us a whole. All right, and so what I'm going to do here is that whole is going to be at negative 3 something. All right, now if I look at my simplified form, I'm going to have x plus 2 over negative 3 times x minus 4. And notice 4 still makes this 0. All right, so after we simplified, whatever value of x still makes your denominator 0, those are going to be your vertical asymptotes. So because of that, our vertical asymptote is going to be at x equals 4. All right, so now the rest of the problem is we now have to figure out, okay, what y coordinate should I have had? Right, so what I want to do is plug negative 3 into this. All right, so negative 3 plus 2 over negative 3 times negative 3 minus 4. And I want to see what value I would have gotten. So negative 3 plus 1 is negative 1. All right, and that's going to be negative 3 times negative 7, which would have been a positive 21. So it looks like we should have had the point, all right, negative 3, negative 1/21. But we don't. We know we had to throw that value out. So that is where the whole would be. All right, so if we were sketching the graph, we go to negative 3, negative 1/21. We draw that little open circle right there. All right, and eventually we'll get to that, all right? Okay, so that wraps up our first part of graphing rational functions that are not in standard form. All right, we'll pick up and continue with this conversation in our next lesson. Be sure to do your video check-in, and I will see you next time.